Our other choice, if our data is not paired, is to use the two-sample t-test, which is really popular. You're going to see these around quite a lot. People use them all the time, but the calculations for them are a little bit more complicated than either the one-sample t-test or the paired t-test. And so if you are analyzing a study that has an unpaired design, your hypothesis is that there's no difference in means between your two sets of samples. And of course, the alternative then would be there is a difference in means between your two sets of samples. If we write that out, our H null is that x bar 1 equals x bar 2, and our alternative is x bar 1 does not equal x bar 2. The equation for the two-sample t-test is x bar 1 minus x bar 2 over the standard error of the mean differences. The standard error calculation is a bit different than what we've seen in the past because it utilizes what's called the pooled variance. And the pooled variance takes into account the variance of both samples and their respective degrees of freedom. In many cases, a two-sample t-test will have equal number of observations, so sample 1 and sample 2 will have the same number of observations, but that does not have to be the case. Sometimes they will be different. To calculate pooled variance, we need to take the degrees of freedom of sample 1 times the variance of sample 1 plus the degrees of freedom of sample 2 times the variance of sample 2, all divided by the degrees of freedom of sample 1 plus the degrees of freedom for sample 2. And so we need to calculate all those things individually and then plug them into that equation. The standard error of the mean difference is therefore the square root of the pooled variance times 1 divided by the n of sample 1 plus 1 divided by the n of sample 2. When we will calculate all this out using an example. If the sample size is the same between the two sets, we can calculate the confidence interval of the mean differences. And the confidence interval would be x bar 1 minus x bar 2, which is the mean difference, plus or minus the standard error of the mean difference times the t critical value based on a alpha of 0.05 and the degrees of freedom of one of the samples, because they will be equal. So now we're going to do an example two-sample t-test, and we're going to use the iris data. And so what we're going to do is we're going to call the iris data. We are then going to compare, let's say, the sepal widths of iris setosa to the sepal widths of iris versicolor. And so here we just subset out those two sets of observations, which you've done in the past, and then we need to take the mean of both of those samples, so x bar 1 and x bar 2. We then calculate our pooled variance. To do that, we need to figure out the variance of our x1, the n of our x1, and the degrees of freedom of x1. Do the same thing for x2, and then we pop it all into the equation for the pooled variance, and you should get a pooled variance of 0.121079, etc. Then we take that pooled variance and plug it into the standard error of the mean differences equation. We run that, and you should get a standard error of 0.0696. We can then plug all of that into our two-sample t-test equation, and we get 9.455. We then need to calculate a t critical value to compare to that t statistic, and so we can run the qt function using a p of 0.05, and the degrees of freedom, just pick degrees of freedom of either sample 1 or sample 2 since they are the same length, since they have the same number of observations, and that gives us negative 2.010 or 2.010 if we are considering the absolute values. Since 9.455 is larger than 2.010, we in fact reject the null hypothesis, and we have evidence to show that the means are in fact different between sepal lengths in Iris setosa and Iris versicolor. We can, since the sample size is the same between the two species, we can calculate our upper and lower confidence intervals using the standard error of the mean difference, and that t theoretical value we've already calculated above, and we have an upper limit of 0.518 and a lower limit of 0.798. Of course, we could always use the built-in function in R. Here, what we need to do is just add our two observations, x1 and x2, and then indicate that the variances are equal. And so var.equal equals true. We run that, and if you notice, we have the same output that we would expect based on our calculations above. All the numbers match. We set var.equal equals true because the assumptions of the two-sample t-test are, 1, that both samples are drawn at random, 2, both populations are normally distributed, and 3, variance for each population is equal. And so we actually assume that variance is equal. However, in many cases, the variances may not be equal in your samples. And if that's true, you just need to run an alternative t-test called the Welch's t-test. And Welch's t-test is the exact same thing as the two-sample t-test, but var.equal equals false. And this is actually the default in R. And so if you run a two-sample t-test and you don't set var.equal, you will automatically get a Welch test. And you can see if we run that, the outcome is very similar to the var.equals true. We can check the normality of our samples using the eyeball test, and we can do that really simply by just running a histogram of our samples. So if we look at histogram of our x1, you can see that looks pretty normal. It looks like a bell-shaped curve. We do the same thing for x2. That also looks pretty normal. It's not perfect, but these tests are very robust to slight differences in normality, so it's okay. It's only if it's really, really not normal that we start to be concerned about it. Now, the other assumption, equal variance, is really important to test to make sure that we use the correct type of t-test. And so one way to do that is to use what's called an f-test to check for equal variance. So it's another statistical test. And the null hypothesis for an f-test is that the variance of sample 1 equals the variance of sample 2, and the alternative is that they're not equal to each other. The equation for the f-test is very simple. It's simply dividing the two variances, but what's important is you need to make sure that the larger variance is the numerator and the smaller variance is the denominator. If we look over here, variance 1 is 0.14 and the variance of 2 is 0.098. So if we run that equation, we get number 1.459, which is our statistic. We then calculate a p-value using the pf function, which includes a q that equals our f value, and then we include the degrees of freedom of our first sample and the degrees of freedom of our second sample, which in this case are the same. And then we also indicate that lower.tail equals false. We're only interested in the upper tail because we are interested if the variances are too different, not that if the variances are too similar. If we run both of those, we end up with a p-value of 0.905, which is much larger than alpha, which is 0.05, and so we fail to reject the null. The variances are equal.